Hello everyone, welcome to TryRide, the new era of learning. This is Pack 365. In Module 2, today we're discussing about depth first search, algorithm in AI, part B. Let's move into the topic. First, what is depth first search? We all know that in previous lecture, we have studied about depth first search, right? So, DFS algorithm is a fundamental graph traversal technique used extensive in extensive in AI, right? It has in various other fields. DFS explores a graph or tree by going as deep as possible along each branch before backtracking. It like exploring a maze by always choosing one path until it hits a dead end, right? Then returns to the last junction to try it another path. So in simple way, we can say like that. Here we have a graph, so A and B. So you can say it starts a choosing node, like root node in a tree, like A, and it marks the current nodes has visited and explore one it unvisited neighbor like B. It travels to the B with unvisited neighbor. So repeat step 2 and 3 until so you mark the current nodes has visited and move explore the next unvisited node of neighbors. And if there are no unvisited neighbors, like all paths from this node is lead to already visited nodes, backtrack to the previous node and try another branch. Right? If I visit B and C and I visit D, if I visit directly A, it will make a loop, right? For the we does not consider a loop, right? So it directly backtrack to the parent node of D, right? C, and it moves to the E. So in this DFS, we have key applications in AI like pathfinding and construct satisfactions like game trees, graph traversals for knowledge, and topological sorting. So pathfinding is nothing but finding a path between two nodes. Okay, so CSPVS like solving the problems like Sudoku or Can Queen by exploring the possible of assignments, game tree like traveling game states to find optimal moves and use specific technique use. So a subgraph S of a graph. G is a graph such that the verticals of S or A, right? The subset of verticals of G, the edges of S or A, the subset of edges of G, right? We have a graph. Subgraph. So what's the condition of subgraph? A subgraph is a part of large graph, right? It consists a subset of the original graph verticals and its subset of its edges, right? Critically, if an edge is an included in the subgraph, its two endpoints must also be included. Example, if we have a graph representing city road, no, we take an example. If you're representing a city road network, like we travel network, like route maps, a subgraph could be just the roads, right? And the intersection which in the specific neighbors, right? We using the left and right turns and locating the landmarks like that. So it travels. So a spanning tree subgraph of G is subgraph that contains all the verticals of the G. So it contains subgraph like we have here verticals and here a spanning tree subgraph. So in that, what is connectivity? A graph is connected if there is a path between every pair of the vertices. Like it has a connection between the outer line. Like if you form a circle loop and we have a outer line, like it is a connectivity, a path between both vertices, and a connected like, like a connected component of a graph G is maximal connected subgraph of G. We said the non-connected graph with two connected components, right? We have separate. So in that we said the connectivity is nothing but it is refers how the connected a graph is, right? We have connected graph, disconnected graph components here. Connected graph means a graph is connected if there is a path between every pair of it vertices, right? So disconnected graph, a graph is disconnected if it is possible to partition its verticals into two non-empty sets, such that no edge connected a vertex, right? In one set or to another vertex, in another, like in one set to a vertex in a order, connected a vertex in a set to another vertex like that. Components or a disconnected graph consist of multiple connections, like multiple connected components with our maximal connected subgraph, right? We have multiple connections, right? We have another path connectivity, like we can say that relevance to DFS, like DFS can use it to determine if a graph is connected and to find its connected components, right? If a single DFS travels starting from the attribute node, like starting node, visited all nodes in the graph, then the graph is connected. Now in the we have format in DFS as trees and forest, right? A tree is an undirected graph T such that T is connected, T has no cycles, right? We didn't have tree, we have tree, and we didn't want to make the circles. This definition of the tree is different from one of the root tree, right? It doesn't form any circle here. So a forest is an undirected graph here, undirected graph without cycle. The connected components of a forest tree are trees like this. So a tree is an undirected graph in which any two vertices are connected by exactly one path, right? Only one path. Or equivalently, it is connected to acyclic graph. They are fundamental data structures in computer science representing hierarchical methods. So a root node is often designed in a tree making right rooted tree. So a forest is a collection of one or more disjointed tree. Like we have here see one disjointed tree, another and one more here. So disjointed trees. In other words, it is an acyclic graph, but not necessarily connected. If a graph is disconnected but has no cycle, it is a forest. Each connected components of the forest trees. Like we have relationship to DFS. When the DFS is applied a disconnected graph, and it produced a spanning forest. Each tree is in the spanning forest corresponding to a connected components of the original graph, right? So we have again a spanning tree here. So a spanning tree of a connected graph is a spanning subgraph that is a tree, right? So a spanning tree is a connected undirected. It is also a undirected graph is a subgraph that is a tree and connected all the vertices together. A spanning tree is not unique unless the graph is true, right? It includes all the verticals of the original graph. It contains no cycles. It is connected. For graph with v vertex spanning, and tree will always have v minus one edges. A spanning tree have applications to design of communication network, right? Relevance of the DFS. DFS can be used to find the spanning tree of a connected graph, and that the edges of DFS travels to the discover new unvisited nodes from spanning trees or a spanning forest if the graph is disconnected. A spanning forest of a graph spanning subgraph is the forest. And here we have concepts of DFS is a general technique for traveling a graph. A DFS travels of the G. Here we also read in this path, visited all the vertices of the edges, and we determined whether the G is connected or not. Computer is the connected the component of the G, and computer is the spanning forest of the G. Like that here, center of the CPU is the main connectivity of the whole nodes. And here we can see and zero DFS on the graph, which n verticals and the m edges, right? So takes the formula of VDE like O n plus n m times DFS can be further extended to solve other graph problems, find and report a path between the two given vertices, find a circle in the graph. Here DFS is a two graph. What Elur talk? It is a binary tree. Here we have DFS. The algorithm uses the mechanism for the setting and getting labels, right? Our vertical and edges. So these are the functions we use for algorithm of DFA input graph and output labeling of the edges of G as discover edges and back edges. So we use the Telegram formulas here. So an algorithm of PSGV, it found the input graph. It has a both we have a like a code. It is a code based. I explain it in depth also. So for the example, we have nodes and lines here. We can see here. So we have A has a unexplored vertex. First we visited unexplored vertex. If we visited the A, it has form a visited circle, a visited mark, visited vertex X, and we have unexplored edges. Like if we don't explore the edge, it will be plain. If we travel the plane, it is a discovery edge. We already traveled to another node by using the edge. Okay. So backtracking, when you backtracking, it forms the edges like symbols the symbols we represented in the DFS. See, we can see here's a B, D, C also non-visited, unexplored vertex here, and A has visited. And after B to C, D, C to D, here we didn't discovered unexplored edges. Here A to B is explored edges like that. We have backtracking like track back. So from A to B, we find if we travel from A, we know how DFS performs here. So if we travel start from A and we visit using we explore the edges and we discover edges to find the route from the B and C and we move to the D, right? From we direct did not consider A to C, right? So we didn't consider A to C because it forms the loop. Like if it take D right now and after A, B, C, D, we form D, right? And here, if we travel from D to A, it's a form a circle. Either what the rule of spanning tree, what the rules of the spanning tree. It includes vertex of the original graph, right? It contains no circles. Okay, so here we didn't want to make circle. So from the come back to the parent like C and it direct explode to the E. E is visited now. Now we completed to whole we completed the whole DFS here. So DFS and Naze Traveler. Right, Naze Traveler is a we say it is a puzzle type. So what it showcase, right? It assumes the no maze traveler is a type of maze travelers. This is a directed and applications like we can say we don't know the route exact or outdoor route, right? Similar and classic strategy and exporting maze. Like if we say represent the maze has a graph where each cell is a node, right? And a path between the cells and edges. We start DFS at the maze entry point, explore adjacent visit unvisited cells. If the exit is reached, right, a path is founded. If a dead end is reached, we used to backtrack like that we use in this maze. So DFS naturally find a path through a maze because it is explored deeply first, right? So strategies mimic how one might physically navigate in a maze going down. One can we say responding and physically navigate, right? Maze going down and until it they get dead end, right? Returns to the then returning to the main backtracking. And while DFS find a path, it does not necessary to find a shortest path, right? For that, but for such is a typically perfected. But in similarly, DFS is a powerful and versatile algorithm that play a crucial role in AI, right? It navigating and understanding the graphs and tree structures, finding paths, identifying connectivities, and solve the problems that can be moderated has state space such its relationship with subgraphs, spanning trees, connectivity trees, and forest, highlighting in its fundamental importance, right, in graph theory and it partially applications. So here we see the maze we have. We can travel by like we do. We comes from the straight here, and after we move left, right, and straight and right, and if we go to dead end, like we can find out the path. If we get the dead end here, we come back again. We find we want to find the route here like I have to take like this. So what I'm telling like this. So I come straight from here, right? So when I come straight like this, so I want to move. If I want to move here, I want to moving left. I get dead end. So I have route to take right and straight and right to straight, like that. If I move here, if I move directly right, I go directly backward. Like I get dead end here. So here I'm making dead end. There is no make sense to move forward, right? So at the time I use backtracking, like I use backtracking here, backtracking, and where I am stopped here, here I was stopped. So I continue from here, like it is a take it as a node point. So I start from here and left. I want to find the root of the here. So try like this. I will come back out. So I find the path direction. I start from here, enter from here, right? I start from here, right? And I come from here, outcome. So like this, we use the path directions. Okay. So in this series, we use the path to find like this. So I hope you guys all are understand about this topic. Thank you.